Log on, tune in, find out. Another good idea from Cambridge.
Yeah, or they can give you advice.
Okay, good afternoon. So let's start. It's a pleasure to have Hatami today, and he will speak about asymptotic extremal graph theory in the dense case.
Thank you very much. I'd like to start by thanking the organizer for such a wonderful program in such a nice city, and more importantly, for inviting me to the program. So I'll start by a very brief and non-rigorous introduction to the talk, and I'll mention that what I'm going to talk about and what kind of results you should expect to see in the talk, and I'll try to justify also the title. This area of asymptotic extremal graph theory has been around for more than a century now. There is this old result of Mantel, which is a very classical result in this area. And since then, a lot of mathematicians contributed to the developments in the area. Turan, Erdős, Lovász, many other famous mathematicians, and especially Hungarian mathematicians, they played a major role in the progress of this area. And if you look at the proofs in the area, there are many clever and very difficult proofs in the that you can find. But very surprisingly, most of these proofs are based only on a handful of techniques. Induction and Cauchy-Schwarz are the main things that you pretty much see in every paper in asymptotic extremal graph theory. And the difficulty comes from combining these few techniques in different ways to obtain the final result. And in recent years, there has been several new major developments which look at this general idea, look at the area from a general perspective and try to understand the general nature of problems in the area. And in particular, there's a work of Friedman, Lovász, and Schreiber, which I think was one of the main things that started this way of looking at the area, and then there were many subsequent works. And this led to discovery of rich algebraic structures underlying these basic techniques, and it had some very interesting consequences. For example, you can rewrite many proofs in a neater way where you don't really care at all about low-order terms. A priori, this is not clear how to do it because they might accumulate to some high-order term in the end. But this way of writing the proofs allows one to ignore those terms. And a very interesting consequence is this way of applying these techniques in semi-automatic and sometimes completely automatic way. So these methods are very easy to program, and one can benefit a lot from using a computer. So what is extremal graph theory? So it's a very big area, but many of the results and central problems in the area, they concern these algebraic inequalities between different subgraph densities. What is the relation between the density of triangle in a graph and the edge density, and these kind of problems? And those are the problems that I'm interested in. And there is this result of Friedman, Lovász, and Schreiber, which is published in 2007, but I think it's a bit older, which shows that every such inequality follows from the positive semi-definiteness of an infinite matrix. So they construct this infinite matrix, and they show that every relation between these subgraph densities follows from this basic fact that this matrix is positive semi-definite. And equivalently, you can restate the result that every such inequality follows from applications of Cauchy-Schwarz, but possibly infinitely many applications. So you can write all possible Cauchy-Schwarz inequalities, and then you can deduce every such inequality from those from that long list of Cauchy-Schwarzes. And inspired by this work, Razborov defined something more refined, which is a general framework, which he calls them flag algebras. And this is a formal calculus which captures many standard arguments in the area, such as induction, Cauchy-Schwarz. So it's a very convenient way of writing the proofs in a neater way. And so the main shortcoming of this theorem is this, that you might need actually infinitely many Cauchy-Schwarzes. And there is a simple observation due to Lovas-Szegedi and Razborov independently, that if you don't want the exact algebraic inequality, if you're allowing a little bit of error, as small as you might want, then finite number of those Cauchy-Schwarzes is enough. So if you want to prove an approximation of your inequality, you can do it by just finitely many applications of the Cauchy-Schwarz. So one of the consequences of these results is that they provide some very neat automatic way of proving these theorems, if you're lucky. And actually, it turns out that we are lucky in many cases. So Razborov, for example, applied this method to Turan's hypergraph problem, which is one of the central, I mean, by many people, it's considered one of the most important problems in extremal combinatorics. And just a straightforward application improves the previously known bounds significantly. Another problem which is studied by many people is the Kachta-Hakwitz conjecture, which again, Jan Hladký, Dan Kroll, and Sergei Norin applied these techniques to settle the not settle the conjecture, but improve the previously known bounds again significantly. And the two other examples that I'm involved in, and I'll talk about more later, is we applied these techniques to a question of which was asked by Sidorenko and independently by Jager, Stovicek, and Andrew Thomason, and we completely solved the question, and also applied to an old conjecture of Erdős, and again we settled the conjecture completely. So those were just applying straightforward computer methods. And now if you also apply this method, and you also, if you're willing to think also a bit, you can do more. Razborov, for example, settled this old problem of finding minimal densities of triangles in terms of the edge density, which will come up in the talk. Another example, again, Razborov solved Turan's hypergraph problem under some mild conditions. And again, we applied these techniques to some classical problems using some extra ideas, and we got some good bounds. And by this, I mean, you have this powerful machine of STB programming. You can use it to check your intermediate steps when you come up with some algebraic inequality, and it helps you to find the proof. So how far can we go? Is lack of enough computational power the only barrier for proving such results? So this is the question that comes up immediately to mind when you just sit in front of a computer and you apply to several conjectures, and you see that you're successful in many cases. And that's what I'm going to talk about in this talk. And actually, this question in different forms is asked by several other people. For example, Razborov, in his flag algebra paper, he states that in his opinion, the most important general problem in extremal combinatorics is the following, that can you prove every such inequality using finite amount of manipulations with finitely many graphs? So it's a very imprecise question, but there are various precise formulations of it by him and Lovas. And I hope that I can, by the end of the talk, I can convince you that we pretty much answer this general question. So now let me be rigorous and give the formal definitions. As I said, in extremal graph theory, we are interested in the densities of different subgraphs in one graph G, in one usually dense graph G. Now, it turns out that equivalently, we can study these so-called homomorphism densities. So let me tell you what are these things. So we have a small graph H and a big graph G. We throw the vertices of H randomly on G. So we take a random map from H to G. It doesn't need to be injective or anything. And we look at the probability that every edge is mapped to an edge. And that's denoted by T sub H of G, and it is called the homomorphism density of H in G. So for example, here, these arrows, they give us a homomorphism because every edge that you look on edge will be land on an edge here. So in other words, why is it called homomorphism density? A homomorphism from edge to G is a map is a function that maps every edge to an edge, and this definition is just the probability that a random map gives us a homomorphism. That's why it's called the homomorphism density. Now, so just a quick example. If you look at this graph on 4 vertices and look at the homomorphism density of an edge, there are 4 possible edges that we can map an edge to, and there are 2 ways for each one exchanging the endpoints. So we get 2 times 4, and there are in total 4 square maps from an edge to this graph on 4 vertices. So we get half. And similarly, we get some number for every other graph. Now, asymptotically, in the dense setting, subgraph densities and homomorphism densities are equivalent. So if you have a sequence of graphs which are dense, and the number of vertices goes to infinity, then you can just exchange homomorphism density with the actual subgraph density, which corresponds to counting subgraphs.
And what is dense?
Dense means that the edge density, there's a lower bound than the edge density, a constant lower bound. Now, but there is an advantage with working with homomorphism densities because they have some nice algebraic structure, or they satisfy some algebraic relations. For example, if you take 2 graphs, H1 and H2, and take their disjoint union, which I denoted this way, then its density, homomorphism density in G, is just the homomorphism density of the first graph multiplied by the homomorphism density of the second graph. And why is that? Because we want to take a map from this graph, random map from this graph to G, and we want all the edges to be preserved. But the edges here are independent from the edges here. So we can just take a random map from here and see what happens, and take another random map from here. So we get this trivial equation. But it turns out that these equations are very useful and they're very nice. So as I said, now we can say that we can translate many results in extremal graph theory to things about homomorphism densities. So let me show an example. There is this classical result of Goodman, which says that if you look at the homomorphism density of a triangle, K3 is the complete graph on 3 vertices. In G, it's bounded below by this quadratic formula in terms of the edge density. So it's an algebraic inequality between edge densities and triangle densities. Now, we can convert every such inequality, every such polynomial inequality, to some linear inequality. And how do we do this? We use a relation from the previous slide. So for example, for Goodman's bound, first of all, we move everything to the left-hand side. And then what do we do with this square? We can just write it as T of K2 disjoint union K2, because we had this multiplicativity relation between different graphs. So you can rewrite Goodman's bound as this linear combination between these 3 graphs, K3 disjoint union of K2, K2, and an edge. So let me give some further definitions. A partially labeled graph is just a graph where some vertices are labeled with distinct natural numbers. So here is an example. We have a graph on 4 vertices, and these 2 red vertices are labeled. This one has label 2, this one has label 3. The only requirement is that they should be distinct labels. Now, remember that we defined this homomorphism density to be the probability that a random map from H to G is a homomorphism. Now, I want to extend this definition to partially labeled graphs. So, take a partially labeled graph H, and let L be the set of all labels. Also, let's fix a map from the labels to G. So, this map will tell us where do the label vertices go. And now I define this homomorphism density of H with this map phi to be the following probability. Again, I look at random maps from H to G, but now I condition on that this random map obeys this map phi. So the label vertices should go according to phi. The rest of them can go randomly. So this phi tells us you can think of it as pinning these labeled vertices on G, and then the rest of the vertices, they can be mapped randomly. And this is, again, we look at the probability that we get a homomorphism. So let's look at an example. So my graph H here is a 2-vertex graph with just one vertex labeled 1. Now the map phi tells me that this labeled vertex should go here. So this is fixed. Now I have the randomness for this other vertex. So there are 6 possible choices because there are 6 vertices. So I have 6 here in the denominator. And 3 of them will give me homomorphism. This one, this one, this one. If this one goes here, I get a homomorphism. The edge will be mapped here. This one will give me an edge. This one will also give me an edge. But the other 3 won't give me an edge. So this will be 3 over 6, which is half. So that's just an example to illustrate the definition. Now, let me also define the unlabeling operator, which takes a partially labeled graph and removes all the labels. So if this is my graph, I can apply this unlabeling operator, and I get the same graph with no labels. Now, what does the effect of this unlabeling with respect to these homomorphism densities? So what is the homomorphism density of this graph here? It's just the probability that if I map everything randomly, I get a homomorphism. But here phi is chosen beforehand, so it's not random. But what if I just take the average with respect to all the random phi's? So let phi be a random map from the labeled vertices to G, and let me take the expected value of this thing. So I should get the same thing as this unlabeling operator, as the same density as the unlabeled version of H. And so if I also let phi to be random, I should get the same thing. So it's a simple equation. Now, remember that we saw that disjoint union behaves nicely with respect to homomorphism density. And this inspires us to define the following equation, or the following notation, that we define the product of 2 graphs to be their disjoint union, because we wanted to respect the homomorphism density. Now, I also want to define the product of 2 partially labeled graphs. So let me first give the definition, and let me explain later why this is the right definition. So what I do is I take their disjoint union and then identify the vertices with the same labels. So some vertices in H1 are labeled, some vertices in H2 are labeled. I take their disjoint union and identify the ones that have the same label. And this way, some multiple edges might arise, but I just replace them with single edge. So here is an example. I have this graph on 4 vertices where these 3 are labeled, and this is another graph. Now I take the union and identify the vertices with the same labels. So 1 is identified with 1, 2 identified with 2, 3 with 3. Now, what happens? So there will be a multiple edge between 1 and 2 because there is an edge here and there is an edge here. I just put one edge here. And between 1 and 3, there should be an edge because of this edge, and so on. And I don't do anything with the other vertices, the blue ones and the ones that they don't have the same labels. So this will be the product. Now, why did I define the product with this way? Let H1 be a graph with labels L1, H2 another graph with labels L2. And phi is a map which tells me where do the labels vertices go in G. Now, I claim that the following identity holds. That if I look at the density of H1 with phi, and then multiply it by the density of H2 with phi, I get the same thing as the density of H1 multiplied H2 and phi in G. So my definition of product of 2 labeled graphs behaves nicely with respect to these homomorphism densities. And why is that? So the map phi already tells us where do the labeled vertices go. There is no randomness involved. And if there is an edge between these labeled vertices which doesn't map to an edge, I'll get 0 on both sides because the edge is present here and also here. For example, if 1, 3 doesn't go to an edge, then here I'll get 0. So those vertices, those edges, they are the same on both sides. What about the unlabeled vertices? The unlabeled vertices, they behave independently once we fix this map phi, because, for example, these two edges, I can just map this vertex randomly and then see where do these things go. And that's the same thing in both sides. So you can think of these as two random variables which are conditionally independent when you condition on these on this part of the morphism. It's the same thing as what we saw for the unlabeled, for the usual graphs with no labels. Now, our goal is to understand these equations for which numbers a1 to ak and which graphs h1 to hk. This inequality holds for every graph G. These are the valid linear inequalities in extremal graph theory. Now, let me try to generate such inequalities. So take some partially labeled graphs, h1 to hk, and let L be the set of all labels involved. Now, also let's take some real numbers, b1 to bk, possibly negative, and the map phi from the labels to G. Now, let's look at this linear combination of this homomorphism density and square it. This is, of course, a positive non-negative number, so we have this inequality with trivially. Now we can expand this thing. We can write it as sum of bi, bj, these homomorphism densities. And then by the equation that we saw in the previous slide, I can rewrite this as T of hi times hj phi. So I get this linear combination of these labeled homomorphism densities, which is always non-negative. Now, so this is what we showed. Now, let me now take the average with respect to all random phi's. So this was for a fixed phi. I can average for all phi. And we know what does this averaging operator do. It just removes the labels. So what I get is that this sum of bi, bj, this densities of hi times hj, and the labels removed is positive, is non-negative. So this is a way of creating such inequalities. Possibly, I mean, not all of them, but at least one way of creating such valid inequalities that hold for every G. Now, let me try to abstract some of these things. So we already know how to multiply two graphs. That's just their disjoint union. So the set of graphs is, we can think of it as a semigroup. We can now look at the algebra generated by them. So the elements are just formal linear combinations of the graphs. So I take these graphs, put some coefficients, and just write this formal sum. And I call this a quantum graph. Now, we call a quantum graph positive if for every graph G we have this inequality. So what I was talking about in this notation would be just we are interested in the set of positive quantum graphs. Goodman's bound, for example, tells us that this is a positive quantum graph. K3 minus 2 times K2 disjoint union K2 plus K2. And we want to understand this cone of positive quantum graphs. Now let me do the same thing for partially labeled graphs. Again, partially labeled graphs, we know how to multiply them. They form a semigroup. So I can look at their formal linear combinations, and this is an algebra. I can multiply them using the multiplication that I already defined for partially labeled graphs. Now, there is also this unlabeling operator, which I can extend it to my algebra. It's going to be a linear operator from partially labeled quantum graphs to the set of all quantum labeled graphs. It just removes all the labels. So we have already seen that this thing is non-negative. That's what I showed in the few slides ago. So this is just the square of this partially labeled quantum graph unlabeled. So in other words, if G is a partially labeled quantum graph, then if you look at G square and remove the labels, you get a positive quantum graph. This is always positive. And since the positive quantum graphs are a cone, trivially for every partially labeled quantum graph, the sums of squares gives us a positive quantum graph. And so the natural question would be, which is amazingly, LOAS has a collection of open problems, like 40 something problems on this topic. And then 17th problem, actually he asks that, is it true that for every f, for every positive quantum graph is of this form? You can write it as the sums of the square. And I asked him, this is a coincidence that it's the 17th problem. It also appears in a paper of Loas and Szegedi. So you can interpret it in the following way, that is it true that every such inequality, every valid inequality follows from finite number of Cauchy-Schwarzes? As I said in the first slide, it follows from infinitely many, but what about finite? And another related question asked by Razborov is that he defined this Cauchy-Schwarz calculus, which is a just formal calculus of doing this complicated Cauchy-Schwarzes, and he asked about the completeness of this calculus. Can you prove every valid inequality using this calculus? And together with Sergei Norin, so all the results that I mentioned are joint with Sergei Norin. I forgot to mention it in the verse in the beginning. We showed that the answer to these questions are negative. So, okay, so this is the result of Friedman-Lowas-Schreiber that I mentioned. And so we can't prove everything, but as I said, we can approximate everything. So the observation of Lowas, Szegedi, and Razborov is that if you have a positive quantum graph, then you can find these sums of squares such that the difference is tiny. It's between epsilon and minus epsilon. So you can approximate every inequality using this method, but not prove it. So how do we prove this? So when we talk about positivity, the first thing that comes to mind is polynomials. So let's look at the situation in the ring of polynomials. So a polynomial in a multivariate polynomial is called positive if it takes only non-negative values. And of course, the sums of squares of polynomials are positive. And Hilbert showed that these are not all the positive polynomials. So there are 3 variable positive polynomials which are not sums of squares of polynomials. And an example is Motzkin's polynomial, for example, which follows from arithmetic mean geometric mean inequality that this is non-negative, but you can't write it as the sums of squares of polynomials. So if this doesn't hold for polynomials, then one can expect that it shouldn't hold also for quantum graphs. And the problem would be to extend these examples to quantum graphs. So we want to construct a quantum graph f, which is positive, but it's not of this form. And the idea is just to take the Motzkin's polynomial and find a way of converting it to a quantum graph and just keeping everything work. So I'm not going to talk about the proof because I'm going to mention a stronger result which implies this. But it's just we define a morphism from ring of polynomials to this algebra of partially labeled graphs and then show that everything works. Being sums of squares, being positive, it behaves nicely with respect to that. But this was expected. Actually, in the paper of Lowas and Szegedi, they say that looking at the analogy with polynomials, we expect that the answer is negative. But we know some things about polynomials. For example, Artin in 27, giving a solution to Hilbert's 17th problem, he showed that every positive polynomial, you can write it as the sums of the squares of rational functions. So it's true that polynomials are not positive polynomials are not necessarily sums of the squares of polynomials, but they are sums of the squares of something nice, the rational functions. So And in particular, this implies that checking the positivity of a polynomial is a decidable problem. How do we check whether a polynomial is positive or not? In one hand, so it's co-recursively enumerable. We just generate all the rational points, say, which is a countable set, and keep checking the polynomial on them to see whether we can make it negative or not. And on the other hand, we keep generating these sums of squares and checking whether p is equal to such a sum. So eventually either we find some point which makes the polynomial negative, or we find some rational function such that we can write p in this form. So this is a decidable problem. So again, Lovaas asks that, even before knowing the answer to the previous question, he asked that, does Artin's theorem hold for quantum graphs? Can you write every positive quantum graph as a sum of squares of these rational quantum graphs that he defined? And one can ask a stronger question. What about decidability? So it might be that Artin's theorem is not true, but still, so one consequence of this would be that the positivity of quantum graphs would be a decidable problem. So let's look at this stronger problem, analog of Hilbert's 10th problem. And so what should we expect as an answer? So it's not, so I want to convince you that it's not a trivial problem. I mean, it's not clear what should we expect in the beginning. So first of all, checking the positivity of a polynomial on this domain it's a decidable problem. It's a continuous domain. It's a semi-algebraic set. If I give you a polynomial, there is an algorithm which tells us whether it's positive or not in this range. And on the other hand, if you restrict your domain to integers, Matiasiewicz's result shows that the problem is undecidable. Given a polynomial, there is no algorithm which tells us whether it's positive on integer points or not. So which situation fits better our quantum graph situation? Which one is a better analog to quantum graphs situation? If you look at the densities, these are numbers between 0 and 1. And actually, they are dense between 0 and 1. So one might think that this is closer to the first problem, which is decidable. But it turns out that no, the second problem actually is the right analog. So what we show is that the problem is undecidable. If I give you an inequality, there is no algorithm that can check it. So this also settles the questions about analogs of Artin's problem.
So does this mean that you have a particular inequality for which there is no algorithm, or that
no,
they exist, or that
there is no general algorithm?
The algorithm works for all of them.
Yes. So as I said, so this also settles the questions about Artin's theorem. So let me talk briefly about the proof. Actually, the proof is very simple, even simpler than the sums of square problem. So we want to prove that this thing is undecidable. If I give you these numbers a1 to ak, graphs h1 to hk, the algorithm cannot detect whether this holds for every graph G. So equivalently, we can talk about polynomials. So because every polynomial, we can convert it to these linear equations. So let me restate the theorem in the following form. The input is a polynomial with integer coefficients and some graphs h1 to hk. We want to know whether this polynomial, where your variable now, the values that they take are just the densities inside some graph G. Is this always non-negative for every graph G? So that's the question. The domain is comes from just the densities inside this graph G. So this is just repeating the same thing. So I'm not going to prove exactly this, but I'm going to prove something similar, which hopefully convince you that this is a difficult problem. It should be undecidable. I prove the following thing. Now, as an input, we get a polynomial in 2k variables. I denoted them by x1 to xk and y1 to yk. Now, the inequality that I'm interested in is the following. I look at the edge densities in G1 to Gk. So instead of one graph G, I have k graphs G1, k big graphs G1 to Gk. I look at the edge densities, I plug them as xi's, and I look at the triangle densities, I plug them as variable yi's. I want to see whether this holds for every possible G1 to Gk. So this is the first step in the proof. The second step, which is technical, is to just convert these several graphs to one graph G, which does this. But this already shows that these kind of problems, one should expect them to be undecidable and difficult. Okay, how do we attack this problem? So it follows from Matyasiewicz's result, it's a trivial reduction, that if you have a polynomial, you can't decide whether it's positive on this domain. So instead of integers, I look at 1 minus 1 over integers. So again, it's a discrete set. These are well-separated points. So you should expect it to be undecidable. Just follows from the Matyasiewicz's result. So I'll take this as my problem, and I give a reduction from it. Now, one of the main gadgets that I'm going to use is this result due to Bolobash and then later Razborov found the exact sharp result, which says that this, remember the Goodman bound, it was a polynomial relation between edge density and triangle density. So this result says that the Goodman bound is sharp only on these points when the edge density is of the form 1 minus 1 over n, where n is a positive integer. So let me say what is this graph here. So the x-axis corresponds to the edge density in G. So it's tk2 of G. So the notation is slightly different from what I use. The x-axis corresponds to these values, and the y-axis corresponds to the triangle densities. Now, what is this gray area? The gray area is the set of all points that we can get. So take a graph G, look at its edge density, and look at its triangle density. It gives us a point. And the point should be inside the gray area. If you take the closure, you get all the gray area. That's the result that the upper bound was known. It's due to, it follows from Kruskal-Katona theorem. The lower bound was conjectured long ago, and it's recently settled by Razborov. And this black curve here, it's the Goodman bound. Goodman bound says that the gray area is above this nice curve, but it doesn't give us the exact thing. And actually, it's only exact on these points 1 minus 1 over n. So we're going to use this result to somehow to simulate these points.
So you're saying that these little humps are all known exactly, are they?
Yes, they are now known exact. That's the Razborov's result, recent result. So, but before that, there was a result due to Bolobash, which was saying that there was another middle curve here, which was separating Goodman bound from the gray area. But the exact thing is recent. Now, let me denote this gray area by S. So S is just this subset of this square. And let G denote this Goodman curve. It's 2x squared minus x. Now, let me give you the reduction. I have a polynomial P. I'll construct another polynomial in these 2k variables in the following way. I take P, multiply it by this thing, which just, it's a way of smoothing it down. Penalize it when xi's are close to 1, makes it smaller. But this is a positive number. And then I add the following to it. I take a big number, which depends on P, but it's easily computable, and multiply it by this thing, sum of yi minus gxi. So this is a new polynomial that I'm constructing. And the followings are equivalent. Let me say what are they. The first thing is p is negative for some xi's of this form. So this already I mentioned that it's undecidable. It follows from Hilbert's problem. So what does this equivalent to? It's equivalent to that q can be negative for some xi, yi's which belong to this gray area. And why is that? So let me check this. It's pretty easy. Suppose that first of all p is non-negative for some xi's of this form. Pi is negative for some xi's of this form. So p is negative multiplied by some negative number. So this remains negative. What about this part? On these points, I know that the Goodman bound is sharp. So I can take these yi's to be equal to g of xi, still remaining inside the gray area. So every yi, I can take it to be equal to gxi. So this sum will become 0. So this will be 0. This is a negative number multiplied by some positive, so q will be negative. So if this is true, then this is also true. Now, what about the opposite? Suppose that q is negative for some points in gray area. I can now, inside the gray area, if my point xi is not in this set, then the Razborov result says that the y should be really separated from g. There is a gap between g and the gray area. So this thing will be a large number. And I'm multiplying it by a large constant to make it even larger. And I'm making this thing smaller by just multiplying this product. So this will be a dominant term. So it's an easy calculus exercise. This will be a large positive number, and this one can't make it negative. So p will also remain. Sorry, what am I saying? I showed that if q is positive, then p also. No, sorry. Q is negative, so this was.
You didn't tell us which sign CP is, so I don't think it matters actually.
It's a positive number, so
Yeah,
big
but
positive.
I don't think it matters because in the previous argument that bit was 0.
Yes, yeah.
You
In
get
this
to
part,
make
it's
your argument work.
yeah. So now I'm assuming that Q is 0. I want to say that P is 0. So this is sorry, P is okay. So the thing is, if Q is negative for these points, then I can move the point towards to one of these 1 minus 1 over n points, and during that I'll only decrease this thing. So in the end, I'll get a point where this is 0 and xi's are in this range, so p has to be negative. So it's just a basic derivative thing.
So this exponent 6 here is because the shape of the humps, is that the point?
Yes, yeah, exactly. Yeah. So you can take anything larger than 6, it's going to work. But so the last statement is just, what does it mean that xi and yi's are in S? It means that xi's are edge density of some graph and yi's are the triangle density of some graph. So that's complete the reduction of what we wanted to prove. Okay, so now let me talk a bit about this applying computer methods to proving results. So, and let me exactly say how do we do it? How do we use computer to prove things? So let's look at the set of all graphs. It's a countable set. Let's just number them, h1 to h2 and so on. Now, let us look at the closure of the following points. This is a very interesting shape. So for every graph G, I look at the densities of different graphs in G. I get a point in 0, 1 to the end. So I get a countable set of points, and I look at the closure. Let's call this R. Now, what does the validity of such an inequality mean? what does it mean that for every G I have this thing? So it just means that this shape R, which is a very monstrous object, is in one side of this hyperplane. So how can I verify that? To understand this question, I need to understand the convex hull of R. So it just means the validity of this inequality is equivalent to that the convex hull of R is on one side of this hyperplane. Now I want to characterize the convex hull. Let's now list the set of all partially labeled graphs. Again, it's a countable set. So what do I know about these densities in G? First of all, for every G, the density of a single node in G is always 1. So let's call this condition 1. The second condition is that if I take any graph H and take its disjoint union with K1 and look in G, this is the same as TH of G because of this multiplicativity. So this condition also holds for every graph H. And the third condition, which is the interesting one, says that if you look at this matrix whose ijth entry is the following, it's the density of Fi times Fj in G. This is an infinite by infinite matrix. It's always positive semi-definite. This also follows easily from the things that we saw before, this positivity of quantum graphs. So we have these three conditions which are easy to verify. And they actually characterize this convex hull. So this theorem, which is follows from this Friedman, Lovász, Schreiber, and then another paper of Lovász and Szegedi later, says that if you give me a point in this space, xh1, xh2, and so on, this 0, 1 to the n, I can tell whether it's in the convex hull or not by checking the following conditions. That I look at this point and the coordinate k1, it should be 1 because of this condition. I check this condition for every graph H, so some coordinates should be the same. And if I construct this matrix, put these numbers in its entries, I should get a positive semi-definite matrix. And these are exactly everything inside the convex hull. So how do I use this to prove an inequality now? So this thing which I call positive semi-definite method is the following. We try to minimize this equation subject to the following conditions, to the conditions that the previous theorem told us. This thing is 1, these are all the same, and this matrix is positive semi-definite. So the previous result says that if I can solve this positive semi-definite program, I'd be able to actually check this. But unfortunately, this is an infinite matrix. So there is no way of actually solving it. But what we can do is we can restrict to submatrices of it. Just look at the graphs on up to certain vertices, say 7 vertices. I get a submatrix of this huge infinite matrix. It's still a constraint. It should be positive semi-definite. So I look at this, I minimize this with respect to this, and I hope that it works and I get a proof. And in many cases, as I said, we're going to get a proof. But in general, we won't, because the problem is undecidable, and also this thing about sums of a square thing, which shows that this is not true always. So this is just the basic template of the positive semi-definite program. It's very easy to implement. So we applied this to several problems. The one is an old conjecture of Erdős. So it appears in print in '82, but I think it goes way back, because I saw a paper from around the same year which was saying that this is an old conjecture of Erdős. But so what does the conjecture say? It says that if you look at a graph which doesn't contain any triangles, then how many 5 cycles can it have? And the conjecture was that it's exactly n over 5 to the 5 when n is divisible by 5. And how do we get that many 5 cycles? We just divide the vertices into 5 chunks, equal chunks, and then put every edge between these chunks in this 5 cycle form. So it's a blow up of a 5 cycle. And the conjecture was that this contains the most possible number of 5 cycles among all triangle free graphs. And so straightforward application of positive semi-definite program solves this asymptotically. To get exactly this number with no asymptotic or limit thing, we needed to do a little bit of more work, but the conjecture itself was, you can solve it using just the computer. Another application is about this common graphs. So a graph H is called common if the density of H in G plus the density of H in the complement of G is always at least 2 to the minus m. So this is a problem which came from Ramsey theory. And Erdős conjectured that all complete graphs are common in 62. Then in 80, Baron Rosta actually extended his conjecture that to every graph. So they conjectured that every graph is common. And Andrew Thomason in 89, he showed that any graph containing K4 is not common. So he disproved both Erdős's conjecture, and of course this one also is disproved. But the interesting thing is that actually those graphs are very rare, and it's very difficult to construct common graphs now. So there are methods of constructing common graphs which use gluing of graphs, this amalgamation of the different graphs. But they can't increase the chromatic number. So what Jagerstowicek and Thomason and independently Sidorenko asked is that, are there common non-three colorable graphs? So every known common graph was three colorable. And the candidate was the wheel with 5 spokes. And actually, both of them mention this graph and say that it's a very interesting question to know whether this is common or not. And this, just again, a straightforward application of a semi-definite programming shows that it's common. So there are examples of non-three colorable graphs, which is the first one is this W5. Okay. So that.
What would Erdős's conjecture have said about the Ramsey number? It would have been a better upper bound on the Ramsey number on the symmetric Ramsey number, right?
It's about I think it would have implied some improved bound, but it's more of a counting version of the Ramsey number. So you take a two coloring of the graph and you count.
So the least copies of red or blue, whatever it is, occur for random colouring.
Yes, that's
very believable statement.
And actually, one interesting thing about this is that what we wanted to do, our original plan was to find a proof for this, try to find a human readable proof, and try to extend it, maybe generalize it to more complicated graph, non-four colorable or higher chromatic number, or at least prove it for all wheels, or all odd wheels. And the proof that we found uses 150 Cauchy-Schwarzes. We tried very hard to simplify it. We couldn't find any way of doing it. When I talked to Razbor first about this, he said that I'm pretty sure I can simplify the proof and find a human readable proof, but then he also gave up. So I think these things are, we should live with the fact that some of these problems probably don't have any easy proofs. It's just, there are just these complicated proofs using big matrices that tells us that they are true, but no hope for finding simpler proofs. So let me also mention some open problems in the area. So remember that this set R was the closure of all these points that we get by looking at densities in this set, densities for all graphs G. So this is a very complicated object. Saying anything about it is really hard. So for example, there's a paper of Erdős, Lovász, and Spencer from 70s where they show that it has non-empty interior if you just look at the connected graphs. And that already is not easy. So it's non-trivial. So one interesting question is due to Lovaas and Schoch, which says that which points of R are unique solutions to these inequalities. So in other words, you can think of it as the following question: which graph sequences are unique solutions to some extremal problem? So unfortunately now it's believed that this is a very difficult question. There was a conjecture, natural conjecture for those points, but it's disproved, and now there are very complicated constructions of those points. So I don't think, there might be that there is no neat solution to this, unfortunately. But another very interesting conjecture of Lovaas is that, so take any such equation which has some solution in R. So probably infinitely many points in R satisfies this. He conjectured that there is at least one point which is finitely forcible. So you can add more and more constraints, only finitely many of them, and reduce your space of solutions to just one point, in other words. Okay, so that's also wide open. And also there are other problems. So as I said, he has this long list of open problems, which 17, one happened to be similar to Hilbert's 17. But, and many of them are open. So I'll stop here. Yes.
Is it easy to check if the proofs are correct? I mean, using computers, of course.
So it's equivalent kind of to matrix multiplication, I would say. So yeah, checking them you don't even need to solve a semi-definite programming or something. You kind of give the certificate, which is a matrix you have to multiply, and you get an equation. But I mean, for the wheel problem, for example, there are 7-digit numbers appearing in these matrices. So it's not understandable, really, but it's easy to check. Yes?
Do you have any good indications of what makes certain problems hard or not? So for example, for Turan's conjecture,
Yes.
I guess Rosbrov's extra solution, which involves forbidding, I think, certain 4-vertex subgraph. So there's a good instance of something which is supporting evidence for Levesque's conjecture. So that's got a unique solution, and that's proved now.
Yes.
So is what makes Turan's conjecture difficult, the fact there are lots of solutions, and thus you'll need lots of equations.
Yeah, that's one thing. If the problem has a unique solution, usually there is a way of reducing your space. So this matrix that you want to look at, this sub-matrices that you want to look at and constraint over, you want to subject to the positive semi-definiteness of some sub-matrix. You can pick this matrix smartly if you know what is the solution and you know that it's unique. But when there are lots of solutions, you usually have no way. You just have to restrict to those big sub-matrix of thing and hope that things work. Yes.
So, do you think there may be an example of an actual sort of simple hypergraph Turan problem which requires infinitely many applications of equation swaps, or can't be done in finitely many applications of equation swaps?
Hypergraphs.
Because I mean, your quantum graph could is pretty complicated, right? And
It involves 9 graphs, I think. But yeah, I don't know if a single graph, a problem of
maybe just involving 2. Do you think that's possible? Or maybe just even involving the.
I don't have any feeling towards. Yeah. Yeah. It might be actually, but I don't know. Yes.
If you take, say, Turan's theorem for triangles, just the density of half gives you a triangle.
Yeah.
Then there's a particular quantum graph, a Goodman graph, whose positivity implies that.
Yes.
You get if and only if statements. So if I give you a forbidden subgraph problem,
Yes.
can you ever, or always, or never find one of your an algebraic statement at densities where positivity is the same as the original statement?
So for graphs, I think yes, because we understand completely the Turan problem, right? Is that your question?
For R is 3. Sorry, yes.
Yeah.
Yes. Hypergraphs.
hypergraphs.
So could it be true that supposing the answer here and everything is always decidable, always, but still extremal densities are not, you can't answer? If you can answer all things about this proportion plus that proportion is positive, does it also imply you can always answer a question which says, in a hypergraph of given density, this object does appear?
So the question is about one graph or one hypergraph. I don't know anything. But if you allow a linear combination of several of them, it reduces to the same thing. But yeah, the case about one thing, I mean, it's very hard to construct a reduction from it. So it might be easy, but my feeling is that it's not.
Very recently, a group around Rosinski in Poland also solved this five cycles and triangle-free graphs. Can you comment on how the proofs are different and what's the strength of each?
So what we prove is more. So
This is a Greshnik paper?
Yes.
They only get the density part, whereas this is a stronger claim that you get the exact result.
So what we get more is the exact result. So it's not just about density. We get exactly the number of edges the number of 5 cycles that you can have. Also, we get uniqueness. So that's what we get more. So what they did was just a straightforward thing from STP program. So that's something that if I tell someone with the program, we can plug it to the program and find the proof. But we did some more thinking with the paper or not the computer.
Does it say anything that if you're close to the maximum number of C5s in a triangular graph, then you have to do similar to?
Yes, yeah, you can deduce that from the proof. So you get the stability.
Okay, so just we can continue the discussion afterwards in private. Thanks a lot.
Thank you.